7. Entropy. Let's dive into one of the most fascinating and misunderstood concepts in thermodynamics, entropy. Many people hear the word and immediately think it means disorder, but there's so much more to it. Entropy tells us about the direction in which energy flows, the limits of what's possible in energy conversion, and why some processes are irreversible. In this chapter, we'll explore entropy in a simple, intuitive way, linking it to everyday experiences like why your coffee cools down but never heats up by itself, or why it's easy to mix things together but hard to separate them again. By the end of this session, you'll see entropy not as an abstract idea, but as a practical tool to understand how nature works and why efficiency always comes with a cost.
1. Learning outcome. Let's start by getting clear on what you'll gain from this chapter. A good set of learning outcomes keeps you focused on the essential skills you'll walk away with. Think of it like your roadmap. Notice how these outcomes are action-driven, using verbs like apply, define, establish, calculate, and analyze. Each word signals something practical you'll be able to do by the end of this session. For example, instead of a vague goal like know about entropy, we use precise actions like define entropy as a property and apply the second law. This approach keeps things sharp and measurable, so you'll always know what you're expected to achieve. Good learning outcomes aren't just a list, they're a promise of what you'll master.
2. Clausius Inequality and Entropy. Let's explore the foundation of entropy by introducing Clausius Inequality. Good explanations always start with the key idea, and in this case, it's simple. Real processes are not perfectly efficient, and this principle helps us measure just how far from ideal they are. Notice how we focus on clear statements like the integral is 0 for reversible cycles and negative for irreversible cycles. This keeps your attention on the practical outcome of the equation, not just the symbols. We also introduce entropy with a clean, short definition, directly linking it to heat and temperature, two things you already understand from previous chapters. By focusing only on the essential takeaways, like what happens during isothermal processes, you won't get lost in complexity. A solid explanation avoids clutter and builds your understanding step by step, and this slide shows exactly how to do it.
3. Entropy generation, an increase of entropy. Let's break down one of the most practical lessons of entropy, entropy generation. A good explanation doesn't just tell you what happens, it tells you why it happens and what it means for real systems. That's why this slide focuses on clear, direct statements like entropy of an isolated system always increases, and entropy of the universe always increases. Rather than getting lost in equations, notice how the slide highlights the meaning behind the math. Irreversible processes create entropy. Reversible processes don't. And negative entropy generation is simply impossible. That keeps your attention on the key concept. You can't undo natural processes without extra effort. This approach strips away the clutter and focuses on what really matters, understanding why nature always tends toward more entropy and how it affects everything from engines to the universe itself.
4. Entropy change of pure substances. Let's focus on simplicity when learning how entropy behaves in real materials. A good explanation highlights what's fundamental. Like here, we see that entropy is a property. That means it depends only on the state, not on how the system got there. This makes it easier to work with because properties stay the same for any path. Next, we avoid clutter by sticking to key equations, like the phase change formula with quality and the straightforward isothermal heat transfer rule. These shortcuts help you solve problems faster without getting lost in complicated derivations. When teaching complex ideas, it's helpful to cut through the noise and emphasize the tools you'll actually use, and this slide does just that.
5. Isentropic processes.
Let's make sense of isentropic processes by focusing on what's essential. A strong explanation highlights the key idea right away. A reversible, adiabatic process is called isentropic. That means no entropy change happens, which makes it simpler to analyze in theory. Instead of overloading you with extra details, this slide keeps it clean. Just the definition, the equation, and where you'll use it. You'll see isentropic assumptions in ideal devices like turbines, compressors, and nozzles, not because they're perfectly realistic, but because they help us get quick, useful answers. Good slides remove the noise and focus on what you need to apply in real problems, and this one keeps it simple and sharp.
6. Property diagrams involving entropy. Let's simplify how you approach property diagrams by focusing on their purpose. Good diagrams act like maps. They help you visualize energy changes without complicated calculations. The TS diagram is your go-to for understanding heat transfer, where the area under the curve tells you how much heat is transferred in reversible processes. And here's a neat trick. Isentropic processes always show up as vertical lines, making them easy to spot. Then we have the HS diagram, or Mollier diagram, which is perfect for analyzing steady flow devices like turbines and compressors. Instead of getting lost in equations, you can see the process behavior at a glance. The goal is to cut through complexity and give you quick visual tools, and these diagrams do exactly that.
7. What is entropy? Let's make entropy simple and relatable. A good explanation always connects big ideas to things you already know. Entropy is basically a measure of disorder, how jumbled the molecules are. Solids are well organized, so they have low entropy. Liquids are more free to move, so their entropy goes up. Gases are totally free, bouncing around randomly, so they have the highest entropy. Then there's the third law of thermodynamics, which keeps things simple. At absolute zero temperature, where molecules stop moving, the entropy of a perfect crystal becomes zero. By focusing on the big picture and using relatable comparisons, we avoid the trap of overcomplication, making entropy something you can actually understand and apply.
8. Differential entropy change. Relations. Let's focus on the formulas that simplify your calculations. A good explanation always gives you the tools to work faster and smarter. The TDS equations are perfect examples. They connect entropy to energy and volume changes without needing complicated process paths. You get two clear forms, one with internal energy and volume, and another with enthalpy and pressure. For incompressible substances, we cut the complexity even further with a simple logarithmic relation. Entropy change only depends on the temperature ratio. The key here is clarity. Instead of memorizing complicated steps, you use these short, direct formulas to solve problems quickly and accurately. That's how you make thermodynamics efficient.
9. Entropy change of liquids and solids. Let's keep things simple when dealing with liquids and solids. A good explanation trims out the complexity, just like here, where we use approximations for incompressible substances. The key formula is short, easy to use, and focuses only on temperature changes because liquids and solids don't compress much. For isentropic processes, the message is even simpler. If entropy doesn't change, temperature stays constant. That's it. You don't need complicated math or long explanations when a single line gets the job done. When explaining technical topics, the best approach is to keep the focus on practical, easy-to-apply rules, just like this slide does.
10. Entropy change of ideal gases. Let's keep things practical when dealing with ideal gases. A good approach gives you two options depending on your needs. When you want a quick estimate, you use constant specific heats with average temperature. This keeps calculations simple and fast. But if you need accuracy, Especially when temperatures change a lot, you switch to variable-specific heats and use entropy functions from tables. This gives you more precision without making things complicated. By focusing only on the two most useful methods, approximate and exact, you avoid unnecessary confusion and get straight to solving real problems efficiently.
11. Isentropic processes of ideal gases. Let's discuss the most useful formulas for ideal gases. A strong set of relations helps you solve problems quickly without overthinking. These isentropic relations are your shortcut. They connect temperature, pressure, and volume with simple exponents, so you don't have to do lengthy derivations every time. Notice how everything is built around ratios. That's intentional, because it makes the equations flexible. You can apply them to any two states without worrying about absolute values. The goal here is efficiency. These three quick formulas will save you time and give you confidence when analyzing turbines, compressors, or any isentropic process. That's how you keep problem-solving sharp and simple.
12 key examples. Let's look at how these concepts apply in the real world. Good examples turn theory into practical understanding. Each example here is short, direct, and focuses on a key lesson, like how entropy increases during isothermal expansion, or how more entropy is generated when the temperature gap is bigger. You also see how entropy helps calculate work in turbines, spot errors and approximations for liquids, and even identify real savings in industry, like the $737,800 per year from replacing a valve with a turbine. The point here is simple. Theory becomes useful when you see it in action. These examples make the topic stick by connecting it directly to meaningful applications.
13. Concluding remarks. Let's wrap up this chapter with a clear takeaway. A strong conclusion highlights the essentials you should remember. Entropy isn't just a textbook idea. It's a key property that directly affects whether a process is feasible and how efficient it can be. We also saw that entropy changes are driven by heat transfer, irreversibilities, and mass flow, factors you'll see in every real system. Isentropic processes, even though idealized, are valuable tools to benchmark and improve actual systems. By cutting out unnecessary detail and focusing on practical impact, this conclusion keeps your understanding sharp and applicable.